really get why people feel such a strong need to defend Die Hard as a Christmas movie. It's obviously a Christmas movie. It has Christmas music in it. It's set on Christmas Eve. There's basically a countdown to Christmas. It has like a Scrooge-like villain. It has family conflict. I mean, what else do you want in a Christmas movie? It's obviously a Christmas movie. You can stop defending it. None of us are saying it's not a Christmas movie. Or maybe you know some crazy person that's saying that it's not a Christmas movie, but they're stupid because it obviously is. It's okay. Calm down. All right, you guys, spoiler alert for some of the scenes in Die Hard. You have been warned. Hello and welcome to another Christmassy Math Monday. Oh, I'm gonna be so sad when these are over. There's technically, after this, only one other Monday before Christmas. Can you even believe that? How did that happen? Can I still do a Christmas video after Christmas? Would that be okay? You'll still be at home with all the Christmas stuff set up, watching Christmas movies. I bet you anything. So it'll be okay, right? So I watched the Christmas movie Die Hard for the first time this week. I know, I watched it, okay? Just back off. So when I was watching the movie, there was one physicsy question I had about the plausibility of the film. Yeah, only one. Why? Is there more than one unbelievable thing that happens in Die Hard? Falling out of an elevator shaft and grabbing onto an air duct? Sounds okay. Jumping off the top of a building with only a fire hose knotted once to hold you? I mean, why not? Right? No, I'm not talking about any of those instances. Today, I want to talk about when John needs to drop something off the 33rd floor and know exactly when it hits the second floor. So today, I'm just going to help him do a few of those calculations. All right, so in a scene in Die Hard, John McClane takes one of those wheelie chairs, some C4, and then for some reason a computer monitor on top of it. That part I don't get as much. Maybe to like tie the C4 to the chair? I don't know. So there's these bad guys on the second floor that are shooting a bazooka or something massive at this like big police vehicle and destroying it and like killing all the people inside. So John is gonna drop this C4 from the 33rd floor and wants to hit the guys on the second floor. The thing is, he's gonna need to know when to detonate because there's still people below him that are hostages, so he doesn't want to detonate too early or else he could hurt them. So when should John McClane detonate the C4? So for this calculation, I need to know the exact distance that the C4 falls. So let's say each floor is about 3.5 meters. For those of you that still haven't switched over to knowing things in metric better than imperial, gosh, why not? That's about 11.5 feet. Now, I know some of you Die Hard fans are like, Nagatomi Plaza is a super schwanky, nice place, and those ceilings look way higher than 11 feet. Well, think about it this way. The nice floors are gonna have 12, maybe even 13-foot ceilings to look really fancy, but then you'll also have just, like the worker ants floors. Some of those will only have like 10-foot ceilings. So I feel like 11.5 feet is a perfect average. So we know that this is falling 31 floors. So we take 3.5 meters and multiply it by 31, and that gets us 108.5 meters. However, you also have to have room for ductwork and insulation in between each floor. So let's say that takes up about a meter per floor. So really, we need to take 1 meter and multiply it by how many floors? 30. Why only 30? Because if you think about it, he's on the bottom of the 33rd floor and it's gonna pass through that ductwork below him, but he wants to hit the bad guys at the second floor, so we don't need that extra bit of ductwork below them in the calculation. So we'll only multiply that by 30 floors, and that's gonna be an extra 30 meters. So the total distance this bomb contraption is gonna fall is 108.5 plus 30 meters, and that's 138.5 meters. Okay, so what else do we know about this? Because at first it doesn't seem like we know a lot, but we know that its initial acceleration is probably just 0 because John gives it some horizontal velocity, but it doesn't look like he really gives it any vertical velocity because really, why would you? You wouldn't want to push down on it or up on it, you just want to push horizontally on it. So there's no initial velocity in the y direction, which is actually really good for us doing the calculation. We can also assume that the acceleration is all just acceleration due to gravity and is therefore 9.81 meters per second squared. So that's the rate at which it's speeding up. So there's a physics equation that we can use for this. That is that distance is equal to the initial velocity times time plus 1/2 times the acceleration times time squared. So at first glance, this doesn't look like a nice equation to use to solve for time because time is in two places. However, I know initial velocity is 0. So if that's 0, then 0 times time is still just 0. So therefore, really, my distance here is just equal to 1/2 times acceleration times time squared. Okay, now I have to rearrange this thing to solve for time. So how do I do that? Well, to get rid of the 1/2 on the right side, we need to multiply both sides by 2. And to get rid of the a on the right side, we have to divide both sides by a because that's the opposite of multiplying by a. So I get 2 times d divided by a is equal to t squared. And to get just t, I square root both sides. So t is equal to the square root of 2 times the distance divided by the acceleration. So if we plug our numbers into this equation, we get 5.31 seconds. Now that's a pretty specific value. So John, I don't think can just estimate this. So do you think he could maybe just estimate 5 seconds instead? And do you think that'd be good enough? Well, let's try it out. So again, we know that distance is 1/2 times acceleration times time squared. So say here our time is 5 seconds. Then what we get is it's falling 122.6 meters. Is that good enough? Well, really, that, if you work it out, is a difference of almost 16 meters from where he wants it. When you have an average of about 4.5 meters per floor, then that's actually going to end up detonating somewhere on the 6th floor, which, I mean, that'll probably still do considerable damage to the bad guys, but it also has a greater probability of doing damage to people on the 30th floor as well. So again, if he really wants that specific, perfect explosion to just affect the bad guys and not so much the people on the 30th floor, then he's got to stick to that 5.31 seconds pretty closely. So I guess next time I watch Die Hard, I'm going to be looking for John McClane's timer. Because obviously, to get it as perfect as he did, he must have timed it. And don't even give me the argument that, oh, he probably just eyeballed it. He looked for when it was at the 2nd floor. You can't see that far down. Your eyes can't do that. He can't just eyeball it and say, oh, I think it's about at the 2nd floor when he's on the 33rd floor. It's not gonna happen. If your eyeballs can do that, I'm pretty sure you're some sort of mutant. I mean, like the good kind in X-Men or something. So congratulations on that. So there you go. That's how we know that John McClane would have to hit that detonator at exactly 5.31 seconds. So therefore must have had some sort of timer with him, or his brain is just like a Swiss Army clock. I don't know. It's possible. He seems to be superhuman in other ways, so maybe that's another way as well. Anyways, that's it for me today, you guys. I hope you enjoyed this Math Monday. I will see you next week for the last official Math Monday before Christmas, but then it might be, another unofficial Math Monday after Christmas. I don't know. I'll figure it out.